Hello everybody. I want to give you guys a little overview of the material for week 2. So what we're going to do is we're going to start off with some early ideas in atomic theory. We're going to talk a little bit more about the evolution of that atomic theory into what we now know as in our modern atomic theory. We'll talk a little bit about the atomic structure and symbolism, how we write out atomic structure. That'll lead us into chemical formulas, and then how we're going to arrange these different elements on the periodic table. And then we're going to talk a little bit about different types of bonding, and then the chemical nomenclature, how we actually write down these different kind of chemicals that we're going to have. So in section 2.1, we're going to start off by talking about the atomic theory of John Dalton. The first concept of an atom came from ancient Greece, and the word came from the Greek word for indivisible. And basically what they were thinking about was like if you had a piece of lead, say, and you cut it in half. Well, then you have two pieces of lead, both with the same kind of properties. But what if you just kept doing that, cutting it into smaller and smaller and smaller pieces? They theorized that at some point you would wind up with a piece that was so small that when you cut it in half, it would no longer have the properties of lead. They were on the right track, but this wasn't really formalized in any way until 1807 by an English school teacher named John Dalton. Dalton's atomic theory has 5 postulates. The first is that matter is composed of exceedingly small particles called atoms. An atom is the smallest unit of element that can participate in a chemical change. It's the smallest unit of an element that has the properties of that element. The second is that an element consists of only one type of atom, which has a mass that is characteristic of the element and is the same for all atoms of that element. So every atom of copper, for instance, weighs the same amount, and that's why every penny of roughly the same size is going to weigh the same amount. His third postulate is that atoms of one element differ in properties from the atoms of all other elements. The fourth is that a compound consists of atoms of 2 or more elements combined in a small whole number ratio. In a given compound, the number of atoms of each of its elements are always present in the same ratio. So he was really trying to explain how we have all this myriad of different materials when we know that it's all based on just a small set of elements. So in our example here, we have copper oxide. We can see that this is composed of both copper and oxygen in a regular pattern. For every copper, there is one oxygen atom, and they arrange themselves together in a definite pattern. The fifth postulate is that atoms are neither created nor destroyed during a chemical change, but they instead only rearrange to make different other compounds. So Dalton's theory led to a very important conclusion here called the law of conservation of matter. If the atoms are neither created nor destroyed during a chemical change, then the total mass of matter present should remain the same. We should have the same mass of products plus as we had the initial reactants. For this chapter, we're going to assume that our chemical reactions completely convert to products. That will make our lives a lot easier. In this case, the initial mass of the reactants is going to equal the mass of the products. In practice, though, reactions really don't go all the way to completion. You always wind up with at least some of the reactants left over. In this case, you're going to have the initial mass of the reactants is equal to the mass of the products, the things that you made, plus the mass of the leftover reactants that didn't react. Next we have the law of definite proportions, or the law of constant compositions. This states that all samples of a pure compound contain the same elements in the same proportion by mass. So we can see that this is illustrated here, where we have equal number in the first example here of green balls and blue balls, and we wind up with a product that has equal number of green and blue balls. In the second example, we have twice as many green balls as blue balls, and we wind up with a product that has twice as many green as blue balls. Constant composition. So we can actually put a little bit of math to that, and we can, in here, if we look at our example here, we took the exact same compound, isooctane, and we had different masses for 3 different samples. When we go and test for the amount of carbon and hydrogen that's contained in it, we wind up getting differing amounts of carbon and differing amounts of hydrogen. But the ratio of carbon to hydrogen, if I divide the amount of carbon by the amount of hydrogen, is always the same. There's always 5.33 grams of carbon for every 1 gram of hydrogen. So they have a constant composition. The next conclusion is something called the law of multiple proportions. This states that when 2 elements react to form more than one compound, a fixed mass of one element will react with the masses of the other element in a ratio of small whole numbers. That's a little confusing, so let's look at our example here. If we have 2 different compounds, both containing chlorine and copper, and we have our green solid and we have our brown solid, if we took the ratios of chlorine to copper and then we divided those two, we see that the brown solid has 2 chlorines for every 1 chlorine that's down here in our green solid. That means that the brown solid has twice as many chlorines. We can picture that here, where we can see here there is roughly 1 chlorine or 2 chlorines for every 1 copper, whereas over here we have twice as many chlorines as we did on the left. In section 2.2, we're going to talk about some famous experiments that led us to the discovery of the subatomic particles that make up atoms. We're going to begin with J.J. Thompson. He was experimenting with cathode ray tubes. These are like these sealed glass tubes where you remove all the air inside of them. They contain 2 metal electrodes which you charge with high voltage. When you do that, something called a cathode ray appears between the 2 electrodes. These were used widely in the past for CRT televisions, those old school televisions, where a cathode ray tube was used to focus the cathode ray onto the glass to make the image. What Thompson discovered is that regardless of the metals that he used for the electrodes, this beam was always deflected towards the positive charge and away from a negative charge. He was able to calculate the charge to mass ratio by figuring out how much voltage was required and carefully measuring how much deflection he had of the cathode ray particles. Here's an image of the kind of setup that he was using. You can see down here he's focusing this cathode ray and then he's able to deflect it using these charged plates here. What did Thompson discover? He discovered that his cathode ray particles were much lighter than atoms. These particles had a negative charge, which is why they were deflected away from the negative charge and towards the positive. These particles are indistinguishable regardless of the source of the material. So that means that they were inside of every different kind of metal that he was trying to use for those electrodes. This cathode ray particle is what we now call electrons. He was focusing on electrons and being able to deflect them. And we now know that these are subatomic particles with very, very small masses, much smaller than the total atom. And they actually do make up all of the different element atoms. They're at least one part. The next experiment was by Robert Millikan with his oil drop experiment. What he was doing was taking microscopic, really tiny oil droplets, and he was able to electrically charge them. He then exposed them to an external electric field, and he was able to slow or even reverse them. Like they were dropping down, and he was actually able to slow them down as they were dropping. And what he was really trying to do was get them to hover there. Because by being able to hover them inside of his apparatus, he could figure out how much charge difference he needed between these two plates. He knew the difference in distance between the droplet and the plates, and he was able to use something called Coulomb's law to figure out the charge on each one of the droplets. When he did that, he was getting values that look something like this in this table. And what he figured out is that all of these values have a common divisor, 1.6 times 10 to the negative 19 coulombs. So what he figured was that there was some sort of particle in there that had this charge, and there were different amounts of these in each one of the oil droplets that was leading to the different charges that he had. Since Thompson had already showed that electrons, we already knew their charge to mass ratio, it's pretty trivial to figure out the mass of the electron then. So we have the coulombs that Millikan found. We can multiply, or actually divide that by the charge to mass ratio that Thompson found here. And we find that an electron weighs 9.107 times 10 to the negative 31 kilograms, which is really, 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 really small. Not much mass at all. The next experiment was by Ernest Rutherford, where he was focusing a beam of alpha particles. These are 2 protons and 2 neutrons together. At a piece of gold foil. He actually didn't know what alpha particles were made at, but he was going to shoot them at this gold foil. He did know that the alpha particles were positively charged. And then he started to look at the scattering. Where did these alpha particles go after they hit the gold foil? So let's take a look at his experiment here. He has his radium here, highly radioactive stuff. Source of our alpha particles. He's focusing this beam out, and what he was really expecting to happen was for these to bounce back, much like a ball hitting a wall. If this is a solid, why shouldn't it just deflect back? But to his surprise, most of these alpha particles just passed right on through. A few were deflected here, and only a very small amount actually bounced back. So what conclusions can we draw from that? He concluded that the volume occupied by an atom must consist of a large amount of empty space. The majority of that material was empty space that allowed the alpha particles to pass right through. He decided that there was a small, relatively heavy, positively charged body that was actually able to deflect, or in some cases even cause the alpha particles to bounce off of. He coined the term nucleus, and he said that this would be at the center of the atoms, much like the sun is at the center of the solar system. He theorized that the nucleus contains most of the atom's mass. Since we already knew that electrons were relatively small masses, is pretty reasonable. And then he said that the negatively charged electrons are going to surround this big nucleus. He also theorized that there was a particle in there called the proton, which was positively charged. This is going to offset the negative charge on the electrons, as we saw that elements are neutral. We can kind of picture what's happening with the gold foil experiment here as alpha particles are coming in. Sometimes they kind of get close to the nucleus and they kind of bounce off in a weird direction. Every once in a while they manage to hit one and then deflect back. But for the most part, they just go straight on through, never coming anywhere near a nucleus. Isotopes. Isotopes are atoms of the same element that differ in mass. So we actually do have elements that have different masses. This is in contradictions to Dalton's theory, but the difference in mass is so minute, he really didn't have a good way of measuring that at the time. In order to justify that, we have neutrons. These are uncharged subatomic particles with a mass that is approximately the same as protons. So in order to get these slightly different masses, we have to have some other kind of particle that has some kind of significant mass that is different between the two atoms, but is not charged. It's not participating and creating charges. In section 2.3, we're going to talk about how to write and interpret the symbols that depict the atomic number, mass number, and charge of an atom. These are used to describe the atomic structure of the atom. We're going to define the atomic mass unit and the average atomic mass, and then we're going to do some calculations. So, as we've seen, the nucleus contains the majority of the atom's mass. Protons and neutrons are much heavier than electrons. Electrons occupy most of the atom's volume. They're actually pretty far away on the scale of this from the center of that nucleus. If the diameter of an atom is approximately 10 to the negative 10 meters, the diameter of a nucleus is only 10 to the negative 15 meters. To put that in perspective, if an electron is flowing around a baseball stadium, the nucleus would only be the size of a blueberry at the very center. And everything in between those is going to be empty space. So atoms and subatomic particles are really small. They have really small values. To make this convenient to write, we're going to define some small units that mean that we don't have to express everything with these really large negative exponents. So we start off with the atomic mass unit, AMU. 1 AMU is 1.6605 times 10 to the negative 24 grams. And this is pretty convenient. So like now the mass of carbon 12, for instance, can be described as just 12 AMUs. And then we have our fundamental unit of charge, which is just the electron. And the electron is going to be equal to the charge of an electron in coulombs. This number that Millikan came up with, 1.602 times 10 to the negative 19 coulombs. So, to give you some perspective here, one proton is roughly 1 AMU, 1.0073 AMU. It has a charge of +1. A neutron is slightly heavier at 1.0087 AMU. It has no charge on it. And an electron is much, much smaller at 0.00055 AMU, -1 charge. Atomic number. So the atomic number is the number of protons in the nucleus of an atom. This is the defining trait of an element. Okay, all elements that have an atomic number that have 6 protons are always going to be carbon. All elements that have, say, 8 protons with an atomic number of 8, those are all going to be oxygen. So neutral atoms. In order for the atom to be neutral, we need the same number of positive and negative charges. Okay? So that means that if you are dealing with a neutral atom, you only have to talk about the number of protons, and then we can assume that there's an equal number of electrons to counterbalance that. Mass number. The total number of protons and neutrons in the atom is called its mass number. So we saw that protons and neutrons have the majority of the mass. When you add them together, really the mass of the electron is negligible. So we'll define their mass number as just the number of protons and neutrons. Also, because they are all roughly 1 AMU, the mass number is going to be really close to the actual atomic mass. So, in order to get the number of neutrons, what we need to do is subtract the mass number, or subtract the atomic number from the mass number. So our atomic number is the number of protons, our mass number is the number of protons and the number of neutrons. Subtracting them gives us the number of neutrons. So when the protons and electrons are not equal, the atom is electrically charged, and we call this an ion. We can figure out what the charge of that atom is by taking the number of protons minus the number of electrons. You can see that if there's more electrons, we're going to get a negative charge. If there's more protons, we're going to have a positive charge. And it's important to realize that atoms are only going to acquire this charge by losing or gaining electrons. They're never going to lose or gain protons in this process, because if they did, then they would be turning into other elements, and that would actually be like nuclear fission, or which we're not really going to get into here. So when the atom gains electrons, okay, it's going to get a negative charge, and we call that an anion, okay? When an atom loses one or more electrons, it's going to get a positive charge, okay, and we call that a cation. To remember which is which here, I've always kind of thought, well, cats are positive, so cations must be the positive one, and anions are the other ones, so they're negative. So chemical symbols. Chemical symbols, you've probably seen these before. They're the symbols that you see on the periodic table. They're used to abbreviate elements. Mercury, for instance, has a chemical symbol of Hg. A lot of them were derived from like really old names that they had for the elements and stuff. Some of them are other languages and stuff. So they don't always make a lot of sense to a native English speaker. But you know, you just kind of remember them. Most of them have either 1 or 2 letters, but as they've been adding more and more elements, few of the newer ones down at the bottom actually have 3 letters. It's important to note that only the first letter of the chemical symbol is capitalized. That's going to be important later when we have to write out various different formulas and stuff. Here is an example that's mercury in a jar with its little symbol, Hg, on it. Here is a list of some of the more common elements and their symbols. So, you know, aluminum, we have Al, bromine, we have Br. Those ones all make pretty good sense, but every once in a while you get something like gold is going to be Au. This is from an ancient Latin word, aurum. Iron is going to be from ferrum. one of the old words for it. And, you know, lead, we have PB from plum bum, which I really like that word. So the symbol for a specific isotope of an element is written by placing the mass number as the superscript to the left of the elemental symbol. And I'm going to show you some examples of that. Down here we have magnesium. We have magnesium 24, magnesium 25. That's going to have one more neutron than magnesium 24. Magnesium 26, it's going to have 2 more neutrons than magnesium 24 and 1 more neutron than magnesium 25. But all of these are all going to have the same 12 protons. Here is a little breakdown of how we're going to write all of the things that we've talked about so far. You put the atomic number in the bottom left here. You're going to put the mass number in the top left here, and you're going to have the charge up here in the top right. And in this book, they typically write it as a number followed by a charge. That's how I'm going to want you guys to do it in the homeworks and stuff when I ask for this. Some other texts, they'll actually write plus and then 2 after that. But this is the way that we're going to do it. So here's an example of isotopic abundance. So we have hydrogen. And hydrogen has 3 different forms. You can have protium with 1 neutron, you can have deuterium with 2 neutrons, or you can have tritium with 3 neutrons. And you can see that they only differ in the number of neutrons that they have, and each one is therefore going to have a different mass. And they also have a different natural abundance. So 99.989% of the hydrogen you come across is going to be protium. Only 0.0115% is going to be deuterium. And tritium is so rare that it's difficult to say even how much there is. We barely ever see any tritium. So we saw that we got to talk now about atomic mass. We saw that each proton and each neutron has a mass of approximately 1 AMU. Each electron weighs far less. Therefore, the atomic mass of a single atom in AMU is approximately equal to its mass number, but not quite. But because most elements exist naturally as a mixture of 2 or more isotopes, the periodic table actually lists a weighted average of all of the isotopes present naturally occurring. That's where these longish mass values that you're going to see on the periodic table come from. So let's see an example of that. In order to do a weighted average, you're going to take the abundance of one of the isotopes and you're going to multiply it by its mass. Then you're going to add that to the abundance of the second one, multiply it by its mass, add that, on and on until you've done all of the different isotopes that element has. We have an example of this in our homework with a video that I did explaining this in a little bit more detail. But let's look at our example here. If 19.9% of boron is boron 10, and it has a mass of 10.0129 AMU, and 80.1% is boron 11, with a mass of 11.0093 AMU, then its average mass is going to be this value here as a decimal times its mass there plus this value as a decimal here times its mass, and that's going to give us an average mass of 10.81 AMU. Little sanity check, we can see that that's between these two values, and it's closer to the one that is more abundant. The occurrence and natural abundances of isotopes can be experimentally determined using an instrument called a mass spectrometer. Basically, the samples are vaporized and then they are exposed to high energy electron beams, and it kind of removes electrons from the sample, making them charged, and then it's focused through onto a detector using magnets. So here's an example here. We start off with our sample and we heat it, and then we hit it with this electron beam and we get it all good and ionized, and then we have these electrodes here that are going to accelerate it out as a coherent particle beam, and then we deflect it with the magnets, and then it hits the detector, and depending on where it hits on this detector, we can tell what the mass is here. So if this has a pretty high mass, then what it's going to do is it's not going to deflect very much, and it's going to strike right around here. If it has a low mass, then it's going to be deflected quite a bit, and it's going to strike more down here. And we can figure out the isotopic abundance if we put in a pure element in here. These are actually used to do all sorts of really great science. A lot of like CSI work and stuff where they inject something in and it tells them everything about who the killer was and stuff. They're using an equipment like a lot like this. In section 2.4, we're going to talk about symbolizing the composition of molecules using molecular formulas and empirical formulas. And then we'll talk about how to represent the bonding arrangements of atoms within molecules. Okay, so the first thing here is we have our molecular formula. This is a representation of a molecular compound which consists of the following. We're going to have the chemical symbols from the periodic table we talked about before, and we're going to have subscripts after the symbols to indicate the number of each type of atom in the molecule. So the subscripts are usually omitted, like we don't put 1 in there as a subscript. Those are usually omitted, and we assume that there's only one of them. The second part is a structural formula, and this actually shows the bonds that are formed and how it's actually arranged. Let's see some examples of that. So here we have our molecular formula. We just have our chemical symbols, and we know that there are 4 hydrogens for every 1 carbon in this guy. Here we can see that carbon is the central atom. It's making 4 bonds to each of these hydrogens. Here we can see this represented in 3D with actual sticks representing the bonds. And then here we have this space-filling one that kind of shows that those bonds are actually due to the overlap of the atomic radii. You're going to see a lot of chemistry represented in this form if you continue to go on into organic chemistry. So many elements consist of discrete little individual atoms, but some of them like to form more complex structures. So a lot of the classic ones are diatomic. So you're rarely ever going to find a loose hydrogen atom. You're always going to find H2, N2, O2, F2, chlorine, bromine, and iodine. These guys are always going to want to find another element nearby, another atom friend, and pair off. Sometimes it's even more complicated. The most common form of sulfur is actually S8, where it forms this kind of twisted ring structure. Here's an example of what the difference is in really the subtle ways that we write things. So if I wrote just a capital H, I would mean 1 hydrogen atom. If I put a 2 in front of it, I would mean 2 individual hydrogen atoms. When the 2 is a subscript after that H, I mean 2 hydrogen atoms that are actually bonded together, forming 1 molecule. Putting a 2 in front of that with the subscripts means I have 2 hydrogen molecules for a total of 4 atoms. empirical versus molecular formula. So the empirical formula indicates the simplest whole number ratio of the number of atoms or ions in a compound, whereas a molecular formula indicates the actual numbers of atoms of each element in a molecule of the compound. Here's my example down here. If we have benzene, the molecular formula is going to show that every benzene molecule is made out of 6 carbon and 6 hydrogens. But to get the empirical formula, what I'm going to do is I'm going to find the least common multiple here of 6, and I'm going to divide both of these by 6, and I'm going to just get CH. Another example would be acetic acid. Here's our molecular formula. You can see each one of these subscripts is divisible by 2. If I do that, I get CH2O. Picturing benzene here for a second, we have this ring structure here, and we can see that the molecular formula indicates all the atoms that would be in this structure, whereas the empirical formula just represents this small piece that is the smallest repeating unit. You can see that the empirical formula describes the piece that's being repeated over and over again as we go around this ring. Here is our example of acetic acid. We can see this structural formula here, and that is going to be the component in just distilled white vinegar. So isomers. It may be possible for the same atoms to be rearranged in different ways. Isomers, compounds with the same chemical formula but different molecular structures. And so an example that we're going to use is going to be acetic acid and methyl formate. They both have 2 carbons, 4 hydrogens, and 2 oxygens, but they're arranged differently. So let's take a look at that. Here we can see acetic acid. We have this central carbon here, 3 hydrogens on it. That's bound to a carbon. Here we have the central carbon, 3 atoms around it, but that's instead bounded to this oxygen right here, which is then bound to this carbon. So even though they contain the same kind of atoms in both, they are structurally arranged differently. They're going to have very different properties because of that. Spatial isomers. So this one's a little tricky. In this case, we have the same kind of atoms. They are actually, for the most part, arranged exactly the same way, except for what they are is they're actually mirror images of this. You could think of this like how your left hand is very similar to your right hand, but they're not superimposable. They're not the same thing. Your left glove doesn't fit on your right hand. And what winds up happening when you turn them back around is, if you pay attention right here, we have this hydrogen that's sticking up towards us, where in this example that hydrogen is actually sticking towards the back. And even though this is a subtle difference, it can actually lead to some pretty substantial differences in properties. A lot of medicines and things of that nature have these properties, and sometimes they can be very medicinal and other times they cannot. One famous example was with a drug called thalidomide. It had a property like this. It had both an S form and an R form. The S form was found to be helpful to women when they were pregnant to avoid morning sickness. And but when they went to distribute it in order to save costs, they left the R form in there as well. And it turned out that the R form actually led to birth defects. So it's very important to recognize these sorts of things and always be very careful with any kind of product that you use in order to figure out, whether or not it's safe. Section 2.5, Learning Objectives. We're going to state the periodic law and explain the organization of the elements in the periodic table. We'll see that you can predict some general properties of elements based on this. And we're going to talk about the difference between metals, nonmetals, and metalloids. So the periodic table was discovered by Dmitry Mendeleev and Lothar Meyer. Basically what they were doing is they were just looking at elements as they went higher and higher masses, and they noticed that every once in a while there seemed to be a pattern that was repeating. So, lithium and sodium have very different masses, but they have similar properties, and they just kept going along and noticing that there's like this repeating pattern in the properties of different elements. They both published their tables in according to increasing atomic mass, and Mendeleev was actually able to use his table to predict the existence of some elements that had not been discovered yet. And when they were later discovered, this provided a lot of support for Mendeleev's ideas that there was something to this sort of periodicity. Here we can see Mendeleev's original table looks very different than the one that we know today. And anecdotally, Mendeleev, great beard. As we move on, we get to the modern periodic table, and one of the big differences is that we started to move away from mass because we started to realize that the relationships really involved the atomic numbers and that we should be arranging the periodic table according to this instead. And so our modern periodic table arranges the elements in increasing order of atomic numbers, and it groups elements of similar properties into the columns, vertically, the vertical columns in the table. So we can see that we have group 1, group 2, group 3. All of the elements in group 1 are going to have similar properties, just like all of the elements in group 18 are going to have similar properties. And there's some additional level of organization that we have here as far as these guys are our metals, these guys are our metalloids, and these guys are our metals, or our non-metals over here. So what are those? Metals are shiny, malleable, they're good conductors of heat and electricity. Non-metals appear dull, they're poor conductors of heat and electricity. And metalloids have properties somewhere in between. They conduct heat and electricity moderately well, and they possess some properties of metals and some properties of non-metals. So we have some classifications that we use. So we have our main group elements. These are elements that are in group 1, 2, 13 through 18. Then you have your transition metals. You're going to find these in groups 3 through 13. And then we have our inner transition metals. These are the two rows at the bottom of the periodic table, the lanthanides and the actinides. We have some additional names for some of the groups. The first group, for instance, excluding hydrogens, are called the alkali metals. Group 2 are called the alkaline earth metals. Group 15 are the pnictogens. The group 16s are the chalcogens. Group 17 are the halogens. And group 18 are what we call the noble or inert gases. Here we can see a visual representation of that. So we have our transition metals, alkaline earth metals, pnictogens, chalcogens, halogens, noble gases, and down here at the bottom we have the lanthanide and the actinide series. In section 2.6 we're going to define ionic and molecular covalent compounds. We're going to predict the type of compound formed from elements based on their location within the periodic table, and we'll determine formulas for some simple ionic compounds. So we've seen that in ordinary chemical reactions, the nucleus of each atom and thus the identity of the element remains unchanged. So electrons participate in chemical reactions, not protons. And that these different reactions are going to happen through the gain or loss of electrons to form ions. If we picture this, we have a sodium atom here. It has 11 electrons. When we remove one, it actually gets smaller. The radius decreases, we get 10 electrons, and it winds up getting this positive charge here because it's lost that negative electron. So the periodic table can help you with predicting the ionic charge that you should expect for the main group elements. Many main group elements lose enough electrons to leave them with the same number of electrons as an atom of the preceding noble gas. So group 1 loses 1 electron, it has a +1 charge. Group 2 is going to lose 2 electrons, it's going to have a +2 charge. On the other side of the periodic table, they're going to want to start to gain electrons. 17 will gain 1, group 16 is going to gain 2. And so let's look at some examples of that. We have calcium here that's in group 2. We'll expect that it's going to lose 2 electrons and it's going to have a +2 charge. Bromine is in group 17. We're going to expect that it gains an electron and it now has a -1 charge. So moving from the far left to the far right in the periodic table, positive charges of cations are equal to the group number. Moving from the far right to the far left in the periodic table, negative charges of anions are equal to the number of groups moved to the left of the noble gases. That doesn't really work for transition metals because they actually can have multiple different charge forms. So let's picture this a little bit. It's a lot easier with it all laid out here. So basically in group 1, right, lithium wants to be like helium. So it's going to lose 1 electron so that it would have the same number of electrons as helium. Similarly, sodium wants to lose 1 so that it can be like neon. All right. Over here, though, oxygen, it wants to gain 2 electrons to be like neon. Chlorine wants to gain 1 electron to be like argon, and so on and so forth. So we get this definite pattern here to how these are going to happen. And then the transition metals are just pretty much unpredictable. We really don't know what kind of charges we're going to find on those guys. So far, the ions that we've discussed have been monoatomic ions. They only involve 1 atom. However, there are polyatomic ions. These are going to be like electrically charged little groups of atoms, and they're going to tend to never really break up. They're always going to be kind of together and moving like a little group, almost as if they were just a single atom when you're kind of arranging things. Here are some common polyatomics. This table is available here and in the book, and this is going to come up. We're going to be working with these as we go through the class, and it's important to start to recognize them when you see them inside of molecular formulas. Let's look at some stuff. There's a system for naming the oxyanions, polyatomics that contain oxygen. When a non-metal forms 2 oxyanions, 8 is the suffix used for the ion with the larger number of oxygens. Ite is the suffix used for the ion with the smaller number of oxygens. When a non-metal forms more than 2 oxyanions, prefixes are used to 8 and ite. So you're going to have per 8 ite, and then hypoite. So an example of this would be like there is perchlorate, then there's a chlorate, then there's chlorite, then there's hypochlorite. All right, so covalent versus ionic bonds. So when electrons are transferred, ions form, and an ionic bond can result. These are electrostatic forces. They're pretty powerful bonds that hold the atoms together. However, when electrons are shared between the two atoms, a covalent bond results. We classify compounds according to what kind of bond they have, whether they have an ionic or a molecular bond. So, metals readily lose electrons. We saw that before in when we were trying to predict the ions that we would see in the periodic table. Nonmetals readily gain electrons. When a metal and a nonmetal react, the electrons are transferred from the metal to the nonmetal. Okay, so that electron really wants to be with the nonmetal more than it ever did with the metal. So metals and nonmetals generally form ionic bonds. And so the compounds that are made from metals and nonmetals are called ionic compounds. Here's an example. We have sodium chloride. When we have one sodium atom, it gives up an electron. Chlorine readily accepts this electron, and we get the ionic compound NaCl, or normal table salt. We can do the same thing with calcium, only calcium is going to give up 2 electrons. So we're going to need 2 chlorine atoms to accept 1 electron for each one. And we get this ionic compound calcium chloride, CaCl2 in this case. So what are some properties of ionic compounds? They're typically solids. They typically have a really high melting point or a boiling point. They're not conductive when they're solids, but when you melt them down and you free up those ions, they're now able to conduct electricity. This has been used pretty extensively in industries for various different purposes. Some of the very first fuel cells were based on molten salt. Ionic compounds do not have a charge themselves. Overall, they are neutral. And what we do is we use this to determine what the ratios between them should be. So if we look at our example down here, we have aluminum with a +3, and we have oxygen with a -2. If one oxygen came over here and bound to this aluminum, it would still have a +1 charge, and it wouldn't be a neutral species. Okay. Similarly, if we just took 2 oxygens and put it over here, well, then I would have +3 and a -4. It would have a negative charge. So what we need to do is find the least common multiple between these two. So what we're going to have to do is have 2 aluminums for a +6 charge here, and we're going to have 3 oxygens for a -6 charge here to ultimately yield our neutral aluminum oxide. So a lot of times, rather than individual monoatomic ions, we're going to have polyatomic ions that we're going to be working with. As we talked about before, the polyatomics are going to be treated as discrete units, and typically they're stuck inside a parentheses in a formula to indicate that they are a group of atoms that behave as one unit. Our example here, we have calcium phosphate. Calcium is a +2. We're going to need 3 of those in order to give us a +6. We're going to counterbalance that with 2 phosphate polyatomics to give us a -6 so that we get our neutral species. And we're going to put these parentheses around the phosphates to indicate that those are all working together as one unit. Covalent compounds. Molecular compounds or covalent compounds result when atoms are shared. They exist as discrete neutral molecules. They're usually formed by a combination of nonmetals. They're often are gases or liquids that are going to boil really easily, or at least low melting point solids. Alright, so in 2.7 we're going to talk a little bit about how we're going to name our ionic and covalent compounds. Alright, so what is nomenclature? Nomenclature is a collection of rules for naming things. Compounds can be identified by both their formula and their name. This is important these days, with all the typing and stuff like that. You can't really put in all those subscripts and stuff and expect that any old person off the street's going to be able to read and understand that. So we're going to have to learn how to name both ionic and molecular binary compounds composed of 2 elements. And we're going to talk about ionic compounds containing polyatomic ions. Okay, when we're naming ionic compounds, we want to name the cation first, followed by the name of the anion. A monoatomic cation, so we only have 1 atom here, is just given the name of the element. A monoatomic anion is given the name of the element with its ending replaced with the suffix "ide." A polyatomic ion is just given the name of the ion. So let's look at some examples. Here we have sodium and chlorine coming together to form a compound, and we call it sodium chloride instead of chlorine. Here we have potassium and bromine, we call it potassium bromide in this case. Similarly over here, we have calcium and we have phosphate, calcium phosphide. All right. Now, when we're doing polyatomics, all right, here we have the ammonium polyatomic, so we call this ammonium, and we still change the last part, chloride, when it comes afterwards. But up here, you'll notice that when we have the acetate polyatomic bound to potassium, we call it potassium acetate. We don't change this to acetide when the polyatomic is the anion. So most of the transition metals and some main group metals can form 2 or more cations with different charges. The charge of the metal ion is specified by the Roman numerals. So we need to be a little bit more specific when we're talking about the transition metals. So because iron can either be a +2 or a +3, we need to, when we're writing out the name, give it these little Roman numerals to tell us what the charge is. So we know that this iron has a +2 charge when we say iron 2 chloride, and this iron has a +3 charge when we call it iron 3 chloride. Hydrates. So a lot of times different compounds are going to have 1 or more water molecules associated with them. When that's not true, they're called anhydrous compounds, and we just name them like we just saw. But when it is true, we're going to add the word hydrate at the end, but we need to add the proper Greek prefix for denoting the number of water molecules. We're going to talk about what those prefixes are at the very end. But here are a couple of formulas for you here. We have copper 2 sulfate, this guy right here. We write a little dot. We see that there are 5 water molecules associated with it, so that is penta, meaning 5, hydrate. Down here, we have our calcium chloride. Get our little dot. There's one water molecule here. We're going to call this calcium chloride monohydrate. So molecular compounds are named using a slightly different set of rules. Basically, there are a lot of different combinations. So we're going to give pretty much all of the atoms participate, or all the names for the atoms participating in a Greek prefix. And we're typically going to start with the more metallic element, the one furthest to the left or to the bottom of the periodic table. Sometimes there's a little discrepancy about which one should be the right one, and you'll actually see things written just a little bit differently on those edge cases. So try not to get too caught up on that. And then we're going to have the Greek numbers are designated for each one of the prefixes. And we're typically not going to use mono. So if there's only one thing there, we're going to skip over it. And when there's two vowels are adjacent, so like basically when the word looks a little weird because you have too many vowels running together, you're going to drop the A from the Greek prefix. The Greek prefix that we're going to use here, there for 1, there's mono, 2, di, 3, tri, 4, tetra, 5, penta, 6, hexa, 7, hepta, 8, octa, 9, nona, 10, deca. It's a little complicated to get into this video all of the different ways that we're going to name covalent compounds, but there are a lot of really great examples in the homework this week and in my homework guide that I would like for all of you guys to look at. Thank you very much for your time. You guys have a wonderful day.